So here we're going to talk about resonance and forced vibrations. But before we do that, we'll review a little bit about the interference of sound waves. Positions of zero displacement resulting from destructive interference are referred to as nodes. We get zero displacement if waves interfere that are out of phase with each other, which means that the crests line up with troughs and the troughs line up with crests. So when those waves add together, a crest plus a trough gives us zero displacement. Like so. So we get no energy at that point, so those are nodes. Forced vibration and resonance. All objects have natural frequencies. So each object has its own natural frequency or its own resonant frequency. And that's the frequency at which it vibrates or oscillates most easily. For humans, that's a pretty low value, probably between 6 and 10 hertz or something. You could look that up. So if we disturb an object, it will vibrate most easily at that frequency, that natural frequency. And that, of course, depends on the properties of the object. So the material it's made of, how large the object is, how long it is, etc. And just about every object you can think of will vibrate or oscillate when it's disturbed, when a force acts on it. So the material, of course, that the object is made from affects the speed of the wave. And as I mentioned, the length will affect those oscillations as well, because that will essentially affect the wavelength with which the object will vibrate or oscillate. And of course, the materials in the object affect the speed of the wave in the object. So all of those factors will affect the natural frequency or the resonant frequency of the object. Tuning forks are one example. Here we have a couple of tuning forks with acoustic chambers attached to the bottom. So this is the acoustic chamber, typically made from wood. And they operate sort of the way that the box on an acoustic guitar operates. They're constructed to be a certain size so that they will resonate when the tuning fork vibrates, when it's struck. What that means is they will amplify the sound. So when you pluck the strings on an acoustic guitar, you can hear the sound quite easily because that wooden box is the correct size, and it will resonate so that the sound is amplified and you can hear it. There's enough energy that you can hear the sound without having the sound electrically amplified, like an electric guitar. So if I set one of these tuning forks vibrating, so if I set this first tuning fork vibrating, then another tuning fork that is the same size, with the same size acoustic chamber, will start to oscillate, and we call those sympathetic vibrations. So that means that we have resonance here. So tuning fork 1 is struck, and without touching tuning fork 2 will start to oscillate. So you can hear the sound from tuning fork 2 because of that resonance. So an object that's forced at its natural frequency will resonate or vibrate or oscillate at that frequency with an increasing amplitude, because amplitude determines the energy of those vibrations. So in order to increase the amplitude of the vibration of the object, we don't have to use increasing force In fact, we could use a very low magnitude force. As long as it's applied at the correct frequency, the amplitude of the amplitude of the vibrations will increase steadily. This can actually be very damaging. For example, if a human is exposed to low frequency sounds at the natural frequency of the body, even if the forces are low magnitude forces, they can do you harm because the amplitude of the vibrations will increase over time. Here's one that's not so damaging. If you have a child on a swing set, to get the child to move on the swing, all you have to do is apply the force at the correct natural frequency or resonant frequency of the swing set. If the child says, push me higher, then you don't push them harder, you don't increase the magnitude of the force, you just continue to push them with the same gentle force, low magnitude force, but you push them at the correct frequency. Typically, one push every second or so. If you push them at 10 pushes per second, well, that's not going to work because that's not the resonant frequency of the swing set. And their amplitude will increase and increase. Now, there's some maximum there because there is some friction involved, and it's unlikely that the child will just swing right over the top. But their amplitude will continue to increase to a certain maximum if you're pushing at the correct resonant frequency of the swing set. Here's a case where resonance can be destructive. If a force is applied, even a low magnitude force applied at the natural frequency of an object, then the amplitude of the oscillations at which the object vibrates can become so great that could be pretty catastrophic. So in this case, the famous Tacoma Narrows Bridge disaster. This bridge was constructed across the Tacoma Narrows in Washington State in the United States, and back in the 40s. And wind passing over the bridge caused low force pushes. So a very small force would push on the bridge over time, and it just so happens that the force was exerted at the resonant or natural frequency of the bridge. So over time, the bridge started to oscillate and eventually started to twist. So you can see in this photograph that the bridge started to twist. And keep in mind, this is a very heavy concrete and steel bridge, so it was a huge amount of energy once that amplitude increased, and it increased to the point where the bridge fell apart. It was destroyed. No one was hurt, to my knowledge, but it was very, very expensive. So now engineers are very careful when building bridges to incorporate structures that will prevent this kind of resonance disaster. Incidentally, you can look up the Tacoma Narrows Bridge. There are old videos you can watch on YouTube, so if you want to pause the video and have a look at those, they're pretty amazing. Standing waves are often visible when objects are resonating. And when it comes to sound waves, we can hear standing waves. And the standing waves have places where there is zero energy. And as we mentioned earlier, those are called nodes. So we see them here. These are the spots where the waves add together to give us zero amplitude. And we have areas where we get maximum energy. Those are the antinodes you see here, where the oscillations have the greatest displacement. So those 0 points, as I said, are called nodes. The points of maximum displacement are called antinodes. And you can see these in a variety of places. If you were to watch a guitar string vibrating in slow motion, which you can probably also do on YouTube, then you can probably see a variety of different standing waves, because that's really what you are seeing on a guitar string when it oscillates. You have a node at either end because the ends of a guitar string are fixed, and you will see, depending on the note that you're listening to, you will see the string vibrating with a node at either end, and you'll see the string vibrating back and forth, and you should be able to see some nodes and antinodes if you do that. So the string's attached at one end of the guitar and at the other end of the guitar, and then you'll see the string vibrating back and forth like so. And you should be able to see some nodes and antinodes. I've seen this also in other places. For example, tall light standards in parking lots. You'll sometimes see this if it's a windy day. I've seen this at the Costco, for example. So I've seen the very tall light standards oscillating, and it looks something like this, where the bottom of the light standard is fixed because it's attached to the concrete base. And I'm exaggerating this a bit, but the top is not fixed, so you can see the top is vibrating back and forth. And it's visible depending on the speed of the wind, and you'll see them vibrating like so. And then about 2/3 of the way up, you'll notice a node. And so if you're in a parking lot on a windy day, have a look at those light fixtures if they're vibrating, or light standards rather, and you may notice that as well. Now it's tough to draw the standing wave while it's moving, and so that's why you'll notice I'm drawing diagrams like this. Sometimes I'll draw them with dotted lines. Sometimes I'll draw arrows to show that the object is vibrating back and forth like so. So the standing wave, if you're looking at standing waves on a guitar string, for example, in slow motion, you'll see that the string is wiggling back and forth, is another way to describe it. So that's what you'll see if you can see a standing wave. If you've done experiments with springs on the floor, then you've probably generated your own standing wave. So how many wavelengths do we see with this standing wave? Well, remember that one complete cycle or one complete wave has a crest and then a trough, and then we have to go back to the start position. So there's the end and there's the beginning of one complete cycle. So if I do that once, like I just did, that's one wavelength. Continuing, crest, trough, and back. So this is 2 complete wavelengths for that standing wave. Now we have a way of comparing the different forms that we see with standing waves. The simplest kind of standing wave looks like this, where we have only half a wavelength, because we have only a crest. So there's a crest, and that's as far as we get. So that diagram represents 1/2 of a wavelength of a standing wave, and we call that the first harmonic. If you're a musician, you may have heard that term before. So the first harmonic is called the fundamental frequency. It's hard to see that, so that's what that says. So fundamental frequency, and sometimes we'll just call that the fundamental. We might say, oh, that guitar string is vibrating in the fundamental, meaning it's the lowest frequency at which it will resonate. So here's, if you were thinking of a guitar string, again, a vibrating string that's attached at both ends, the first harmonic would look like this, second harmonic would look like that, and the third harmonic would look like that. Notice that in each case we have to have a node at each end because it's a string, which means that it's attached to something at either end. We couldn't have an antinode at the end of the string. So here we have the wavelength of the first harmonic. So the wavelength of the first harmonic is 2 times the length of the string, because as we saw earlier, this is only half a wavelength that's shown here. So if we wanted to find the whole wavelength, we'd have to say, well, that's going to be twice the length of the string. So this is L, the length of the string, but I know that I'm only showing half a wavelength, which means that that lambda, the wavelength, has to be 2L, because this is also L. So that means that the frequency is speed over 2L. And you recall that comes from the universal wave equation, which tells us that speed of the wave equals frequency times lambda. which means that frequency is equal to speed over the wavelength. So that's where we got that from. Trying that for the second harmonic, well, we see one full wavelength here now, so wavelength is equal to L, which means that frequency is equal to speed of the wave over L. For the third harmonic, we have 1.5 wavelengths, or 3 lambda over 2. So when we rearrange that, we get lambda is equal to 2L over 3. So the frequency must be equal to 3V over 2L. Like so. So you can probably see a pattern here. Going from the first harmonic to the second harmonic, the frequency is multiplied by 2. And going from the first harmonic to the third harmonic, the frequency is multiplied by 3. So this is times 2, this is times 3, and we would continue if we went into higher harmonics than that. Let's try a practice question. A string resonates with a fundamental frequency of 512 Hertz. The speed of sound in the string is 1,750 meters per second. What is the length of the string? So, if we use our universal wave equation, we know that the speed of the wave is equal to f times lambda. So we have lambda is equal to v over f. And we get 1,750 meters per second for the speed. We'll substitute that in, divided by 512 hertz for the frequency, and we get 3.418 meters. If this is the fundamental, which we are told it is, then that means that it's oscillating in the first harmonic. In the first harmonic, with the first harmonic, we have the length of the string is equal to half the wavelength. And so we'll substitute the wavelength in, and we get 1.71 meters for the length of the string. Let's try a guitar string now. It has a frequency of 256 hertz and a length of 49.1 centimeters. I believe 256 hertz is middle C. If you're a musician, you can confirm that for me. The guitarist reduces the string's length by 12.8 centimeters by pressing on the string. What is the new frequency? Okay, so for the first length, we can use the universal wave equation, V equals F lambda, and we know that the wavelength is equal to 2L in this case. So we have 2 times the length of the string times the frequency. And here we're assuming that the guitar string is vibrating in the first harmonic, so that's why we are using 2L for the wavelength. So when we work that out, we get 251.4 meters per second for the speed of the wave in the string. And to get the frequency, we can take the speed and divide by the wavelength using the universal wave equation again to get the new frequency. But we have a new length here. So we take the old length and we subtract the 12.8 centimeters, because that's what we're told we're doing when we press on the guitar string in this example. Notice that I've converted to meters because we need to use meters for our wavelengths if we're using hertz for frequency, which we are. And we get the new frequency is equal to 346 hertz when we work that out. So reducing the length increased the fundamental frequency of the guitar string. So when you decrease the length of the guitar string by pressing your finger down on the string, the closer your finger is to the bottom of the guitar, so the shorter you make that string, the higher the frequency. So if you've ever seen a guitarist playing a guitar solo, you'll notice that they have their fingers way down at the bottom of the guitar to get those really high frequency or high pitch sounds. They want that string to be really short in that case. Eddie Van Halen was really famous for that. You young folks won't remember Eddie, but he was a great guitarist. Still is, I'm sure. All right, let's try some practice. So you can try these. And it's probably a good idea if you look up some examples of resonance of waves on YouTube. You can probably find lots of good ones. Guitar strings are pretty fun to watch. So have a look at some of those in slow motion.